Can a machine learn to see sounds or taste colors? That is the core idea behind artificial synesthesia systems. AI models designed to mimic the human phenomenon of synesthesia, where stimulation of one sense triggers another, like hearing colors or seeing music. In humans, synesthesia is a rare but real condition, often blending sight, sound, and emotion in unexpected ways. Now, researchers are exploring whether artificial intelligence can develop similar cross-sensory perception using deep learning to create multimodal systems that link visual, auditory, tactile, or even olfactory data in creative, human-like ways. How could this work in practice? AI can be trained on paired data sets, for example, images and sounds that frequently occur together, allowing it to build internal associations between senses. Over time, these models begin to generate new outputs that cross sensory boundaries, visualizing a voice, composing music from a painting, or translating textures into sounds. Example, some neural networks can create artwork based on emotional tone in speech or simulate touch sensations from visual cues. Analogy, it is like teaching a robot to dream in color using the rhythm of a heartbeat. Artificial synesthesia may one day enhance art, design, accessibility, and even empathy, allowing machines to interpret and express the world in more human-like, emotionally resonant ways. How can AI models, grounded in discrete digital data streams, cultivate cross-sensory associations, like seeing sounds as colors or hearing images as textures? In a manner reminiscent of human synesthesia arises from atypical neural cross-wiring, causing stimuli in one sensory modality to trigger experiences in another. In AI, the goal is to engineer architectures that learn analogous cross-modal mappings, enabling a machine to translate auditory inputs into visual representations or to taste the sentiment of text. So far, so good until we examine the challenges of building these associations in artificial systems. The artificial synesthesia systems scenario emerges when deep learning models trained on paired datasets of images and sounds or text and haptic feedback attempt to fuse modalities through shared latent spaces. In theory, a well-trained model could generate a colorful spectrogram from a melody or evoke a tactile pattern in response to a spoken phrase. Yet in practice, ensuring that these mappings reflect meaningful, consistent cross-sensory experiences, as opposed to arbitrary statistical correlations, reveals fundamental tensions between data-driven learning and genuine perceptual integration. At its core, implementing artificial synesthesia is an exercise in multimodal representation learning. Architectures such as variational autoencoders or contrastive transformers seek to align embeddings from different modalities into a unified feature space. During training, the network adjusts so that inputs with shared semantic or emotional content co-locate in this space, ideally producing coherent cross-modal outputs. However, this approach assumes that semantic similarity implies sensory compatibility, an assumption that can crumble when, for example, a melancholic violin solo is mapped to images of cloudy skies. The model's output may satisfy a statistical loss function without evoking a consistent, human-like synesthetic experience. Yet even the most advanced multimodal models exhibit brittle behavior under closer scrutiny. Small shifts in the training distribution, such as introducing new instruments or dialects, can cause this synesthetic mapping to break down entirely, yielding visual artifacts that bear little relation to the input sound. Likewise, adversarial perturbations or noise can send the model's outputs careening into unexpected sensory spaces, akin to a human synesthete suddenly perceiving jarring color shifts when hearing a familiar word. These breakdowns underscore the paradox that while AI can learn to approximate cross-modal associations, it lacks the embodied context and neurodevelopmental grounding that give human synesthesia its stability. At even finer scales, the interactions among model components reveal deeper limitations. The self-attention layers that fuse auditory and visual tokens capture statistical co-occurrences, but do not encode causal relationships between sensory experiences. As a result, an AI might consistently render the word lemon as a bright yellow texture in one context and as a muted green gradient in another, depending solely on dataset biases. Human synesthesia, by contrast, exhibits remarkable consistency over time, suggesting that genuine cross-sensory perception relies on stable neural circuits and lifelong reinforcement, not just on pattern alignment. In essence, artificial synesthesia systems expose the boundary between pattern recognition and authentic perceptual integration. While AI can be coaxed into producing fascinating, cross-modal artifacts, these systems remain fundamentally different from biological synesthetes, whose experiences are rooted in the brain's intrinsic wiring and developmental history. Much like the hysteresis paradox reminds us that memory shapes system responses, and deep-sea submersible failure highlights the fragility of interdependent subsystems under stress, artificial synesthesia reveals that true cross-sensory perception demands more than statistical mapping. It requires embodied context, continuity, and the robust neural scaffolding that only biology provides. Artificial synesthesia systems explore whether AI can form associations across sensory modalities, such as linking sounds to colors or textures to tastes. Similar to human synesthesia, these systems rely on algorithms that map features from one sensory domain into representations of another, creating cross-modal experiences by training on paired multimodal data. AI learns statistical correlations that can mimic the involuntary sensory blending observed in some humans. This challenges the assumption that perception must remain siloed within individual sensory channels. A neural network trained on videos with audio-visual alignment can generate a color palette based on a musical input, producing consistent color themes for specific melodies. It is like a translator who not only converts words between languages, but also conveys the emotional flavor of a poem as a sequence of fragrances. Human synesthesia is a neurological condition where stimuli in one sense automatically elicit perceptions in another, such as seeing shapes when hearing music. AI cross-modal learning, by contrast, is a deliberate training process where models learn to predict or generate data in one modality from another via supervised or self-supervised objectives. While human synesthesia is involuntary and idiosyncratic, AI systems can be designed to produce consistent and controllable cross-sensory mappings. This distinction highlights both the parallels and the differences between biological and artificial sensory integration. Grapheme color synesthetes always perceive the letter A as a specific hue, whereas an AI model can be tuned to map A to any chosen color scheme. It is like comparing an artist's spontaneous color associations to a graphic designer's deliberate application of a style guide. At the algorithmic level, crossmodal AI leverages joint embeddings, where data from different senses are projected into a common latent space. Neural networks use layers of nonlinear transformations and attention mechanisms to align these embeddings, capturing multimodal correlations. This shared representation allows the model to infer one sensory attribute from another by traversing the latent manifold. The process reveals that sensory information can be encoded abstractly, independent of its original modality. Clip models embed images and text into the same vector space, enabling caption generation from visual inputs and vice versa. It is like organizing a multimedia library by theme rather than by format, so that photos, songs, and articles about sunsets all cluster together. Transformer architectures use cross-attention layers to fuse information from multiple modalities, letting the model weigh how each sensory input informs another. During training, attention scores highlight which features, such as visual textures or acoustic frequencies, are most predictive of the target modality. This dynamic routing of information underpins the emergent synesthetic responses as the model learns to attend to relevant cross-modal cues. Consequently, AI can generate sensory predictions that feel intuitively linked, even if the modalities differ widely. In a text-to-audio model, cross-attention guides the synthesis of soundscapes that match a written description of a bustling market. It is like a conductor synchronizing multiple instrumental sections to create a coherent symphony from disparate musical voices. High-quality, aligned multimodal datasets such as video clips with transcripts, audio recordings with visual context, or taste-text pairings are crucial for teaching AI cross-sensory associations. The diversity and scale of training examples determine the richness and fidelity of the synesthetic mappings. Biases or gaps in these datasets can lead to skewed or superficial crossmodal behaviors. Ensuring broad coverage of real-world sensory pairings is therefore essential for robust artificial synesthesia. A dataset of food images paired with flavor descriptions enables an AI to suggest taste profiles based on visual cues alone. It is like teaching someone to recognize spices by sight and smell using a richly stocked spice rack rather than a single jar. Non-linear activations in deep networks allow small patterns in one modality to trigger large responses in another, producing emergent synesthetic effects. These non-linearities can amplify subtle correlations, such as a particular chord progression correlating with a color gradient, into vivid cross-sensory outputs. Such emergent associations often surprise designers, revealing hidden structure in the data. An audio-to-image model may generate abstract art that stylistically echoes the emotional tone of a song in unexpected visual forms. It is like mixing musical notes to create a perfume, where the final scent evokes the harmony rather than any single note. Artificial synesthesia opens new avenues for creative expression by enabling artists to compose multisensory works, painting with sound or sculpting with light. In accessibility, these systems can translate visual information into audio for the visually impaired or convert speech into tactile patterns for the hearing impaired. By blending senses algorithmically, AI expands the palette of human-machine interaction. This cross-modal creativity and utility echo human synesthetic experiences but on a programmable scale. A synesthetic art installation might convert live piano performances into projected color fields that evolve with the music. It is like a translator who simultaneously interprets a speech into sign language, descriptive audio, and braille. Modeling authentic synesthetic impressions requires careful curation of training objectives to avoid superficial or culturally biased mappings. Ensuring that AI-generated cross-sensory outputs are meaningful and not merely arbitrary associations is a core challenge. Ethical concerns include respecting neurodiverse synesthetes' experiences and avoiding the erasure or commodification of genuine human sensory conditions. Responsible development demands inclusive datasets, transparency, and user-centered design. An AI that arbitrarily maps human faces to unpleasant sounds could inadvertently stigmatize certain visual features. It is like building a universal translator without accounting for cultural nuances, resulting in awkward or offensive misinterpretations. Future research will explore more intricate multisensory models incorporating taste and smell, potentially leading to fully immersive virtual reality experiences. Advances in neuro-inspired architectures and neuromorphic hardware may bridge the gap between artificial and biological synesthesia. Understanding and replicating cross-modal perception could also shed light on human cognition, offering insights into how the brain integrates sensory streams. Ultimately, artificial synesthesia systems may redefine the boundaries between senses, creativity, and machine intelligence. Prototype VR systems are being developed that combine haptic feedback, scent release, and dynamic lighting to simulate tasting a virtual fruit. It is like orchestrating a multisensory theater where every line of dialogue is both heard and felt.